Okay, I want to. Okay, I want to welcome everybody to our distinguished lecture series. Our distinguished speaker today is Steve Oberlin. It's my great pleasure to introduce him. He's Chief Technology Officer at Accelerated Computing at NVIDIA. Steve has had a long, distinguished career in large-scale computing. He worked at Cray Research, starting in the 80s. He worked on Cray 1, 2, and 3, and then he was the chief architect for Cray P3D, and then Cray P3E. He holds several patents for architecture and design of the Crays. He then became VP of Hardware Engineering for Cray SDI, one SDI and Cray Bells. Okay, then in 2000 he was at Unlimited. He founded Unlimited Scale, which was providing computing infrastructure for CASAT and CA technologies. And then in 2013 he joined NVIDIA and as Chief Technical Officer for Accelerated Computing. Today he's going to talk to us about machine learning and GPUs and applications, how they all come together. So let's welcome Steve.
Thank you. I'm actually a little intimidated. Normally I like to talk to people who don't know very much. It makes my job a lot easier, so I'm a little worried. So I'm going to start out. Is this too loud? Okay. So I've spent most of my life in high-performance computing, and one thing that I've noticed over the years is that even though lots of really great science has been done using supercomputers as simulation engines to simulate, globular clusters and material science and improve the efficiency of airfoils and turbine blades. We don't necessarily experience those benefits directly. Maybe weather prediction and somewhat more efficient automobiles. It's not as direct an interaction with technology as other areas of technology. In particular, if we think about now, I'll bet if I went around the room and checked everyone's pockets, pretty much everyone has a smartphone in your pocket. And this started in 2007 when Apple introduced the iPhone. This was the beginning of people starting to carry around a portal into the cloud, into data centers. Steve Jobs was initially opposed to allowing people to write applications for the iPhone. Apple delivered a few utility applications. And his vision was that people would basically use web apps. Basically, you'd put an icon on your home screen, and you touch that, and it basically takes you to an HTML application, something running in the cloud. Apple eventually relented and opened up the developer tool set, and there was this explosion of apps, right? So, thousands and thousands, maybe 1 million by now. Applications were developed. There's an app for everything. The most amazing part of this, perhaps, is how many applications I downloaded onto my phone and only used once, and I have pages and pages of those. Maybe the second most amazing thing is that, for once, the user interface became so natural that, even my mother could install, download and install an application on what is a real computer. But the reality is that when you look at what happened after the big app rush, by a year ago or so, we started to see that there were a few applications that became much more important to us than most apps, because really they were cloud apps. They were portals into massive data center hosted services that provided search, They provided networking, social networking. They were places for us to upload and share photos and our experiences of our life, et cetera. And as a result of that, I think Steve Jobs' original vision has somewhat come true, but we've also then become part of the business model for the companies that are providing these services. And the way this works is, we're basically collecting data just by carrying around their application and interacting with it every once in a while. They're gleaning information from us, and that becomes part of the service that they provide. They know your location, they can help give you directions. They can make recommendations about where you might like to eat. They can, build up a recommender about what movies you like, or, all kinds of preferences. They can start to curate the news feed and the comments and things that you see. We can start to shape the flow of data that's being directed at us, because we're the sensors. We're the basis of big data, really. And in return, we get something back for free, right? Quote unquote free. We have to watch a lot of advertisements, but in return, really, we're now extended by this. We're in better contact with family and friends. We're able to access information that was completely unthinkable even 5 or 10 years ago. We're all cyborgs now because we're carrying these portals into these massive data center hosted capabilities. And this isn't necessarily a bad thing. So what this has resulted in is what everyone calls the age of big data. And they talk about big data a lot of times as being a problem. How big is it? It's really, really big. Some estimates put the amount of web data that's created every day at over 3 exabytes. Who really knows? Facebook knows over 350 million images are uploaded every day, and YouTube knows that over 400 hours of video are uploaded every minute. So good luck following your favorite channels there. How can we make use of that data, right? It's so much data. We have an interest in some of it. There are things we want to learn. The companies that have this data, that are hosting this data, want to be able to gain insight from it, but it's unlabeled or it's badly labeled. You can tell just by doing some searches. If you do a text search just on the metadata, kind of the traditional way of identifying what a particular field in a database might be, you can search for images, man texting, and because a lot of people have uploaded photos, stock photos that they want people to use or buy, you get reasonable results. And just to show it's a gender-neutral world, you get the same thing if you look for images of woman texting. But if you type in something a little bit odd, you don't necessarily get results that make very much sense. And people take pictures of their car and intentionally mislabel it when they upload it. Somebody might really like their car and they upload a picture of it saying "my baby" to Facebook. And so how is AI supposed to make sense of that? It's only pixels. These things are just gradations in color. How do you get structure out of those? It's been a problem for a long time. So in around 2010, a large labeled data set was created by ImageNet, and they started a competition. They basically paid people a few pennies per image to draw boxes around everything in an image and label it from some 22,000 different categories of objects that they had predefined. And then they started a competition called ImageNet for the computer vision community to compete in, to basically try to, in a couple of different categories, identify everything that's in a picture. So they reserved some set of these images that had been correctly labeled by people to use as the test case, and they made the majority of the images available to contestants to train their models or sharpen their hand-constructed classifiers. And if you look back over the history of computer vision over the last couple of decades, it's been a very slow progression towards an okay result. Maybe a 25% error rate, and up to 2012, the amount of progress that was being made every year was pretty small. In 2012, though, Jeff Hinton and his group of researchers from the University of Toronto entered the competition with a deep neural network, convolutional neural network that had been trained on really large, on the large data set with a really big neural network. And they were able to make remarkable progress, and it really completely changed the course of the competition. Over the next 3 years, pretty much because Jeff Hinton and his team did all their training on GPUs because it was the only way to accomplish it in a reasonable amount of time. Pretty much all of the contestants switched over to GPUs, and pretty much all of them switched over to using deep neural networks. Researchers were abandoning their life's work in hand-tuned image classifiers. And over the next couple of years, progress proceeded at a remarkable rate down to the point where a person actually trained themselves and took the test to try and establish a baseline. And they got a result of 5.1% error rate. And actually now Google and multiple contestants have surpassed what this person achieved. So we could arguably say that at this point, a computer can, at least on this set of images, correctly view and classify everything that's in those images at a superhuman level of skill, right? Better than a person can do. So I don't want to be remedial, but basically a deep neural network is just a many-layered artificial neural network. The way they get trained, actually, and if you analyze the weights and look at the kernels that get trained in the first convolutional layers, it actually starts to resemble how we theorize the human optic nerve and the first layers of the retina pre-process images before sending a higher level representation down the optic nerve. So initially in the first layers you have very simple edge detector kernels that get trained, and then higher levels build up a hierarchical representation that eventually starts to look like faces. And so even when you train neural networks for multiple different classifications of images that you're trying to recognize, faces, cars, elephants, chairs, if you look at the lower level representations that the network learns, the lower levels, you see that basically they all have very similar kinds of hierarchical feature recognition. This is an actual AlexNet deep neural network. It has a couple of convolutional layers, starts from a random initialized state. The first few initial convolutional layers then go into a couple layers of fully connected classifiers on the very end of the network, and then this gets necked down to this 22,000 classifications that come out of it. And so you can see as the training starts, everything's kind of gray, and then it starts specializing in this hierarchical way. This is the backpropagation training algorithm at work that is not a new algorithm, but it's being applied to dramatically large models now that have many, many layers, far in excess of what existed previously. So just a little more on this. We shouldn't be confused. These deep neural networks don't actually resemble how human nerves function or how brains are organized. They're bio-inspired. A deep neural network, if it's sufficiently large, it can be described as being, kind of a universal nonlinear function approximator. And there's several different kinds of architectures, but they all use basically the same training algorithm. And they're only semi-understood. There's a little bit of an art to training them and initializing them and getting them to converge. And so it's pretty important that you can enable some trial and error. So having a training cycle that takes 2 months is unacceptably slow, very difficult to make forward progress. I want to contrast this because you may have heard of neuromorphic computers or spike timing dependent plasticity models of spiking neural networks. These are the guys who are trying to actually build direct analogs of how brains work and how brains are organized. And we're making great progress there, but it's a long way from being commercializable. There's some really cool aspects of it, like in inference mode. In other words, not being trained, but you're just recognizing things. It can be incredibly low power, which is sort of like the brain, right? We have, hundreds of billions of neurons with tens of thousands of connections each, and your brain is many orders of magnitude larger than the very largest neural network, and yet we're only consuming a handful of watts at any given time, some of us more than others. So that's a really interesting field, but it's kind of like flapping wing airplanes versus trying to understand the principles behind flight and build airplanes. So just a little bit of history, because if you're, and a lot of you aren't, I was going to say older than a couple of decades, you may have realized that there have been a couple of prior waves of excitement and hype about neural networks. The actual basic idea is really old. In the 50s, there were actually a couple people who came up with similar kinds of things. The perceptron, 1957, Frank Rosenblatt. A lot of people got really excited because, wow, you could train this thing to recognize things. And it was just a single layer model that basically has kind of a threshold accumulator here, and it has a weight associated with each input. And those are your data inputs, and you adjust the weights in the training process by some algorithm until finally you get a positive result out of the thing. And it's this adjusting of the weights that lies at the heart of all neural network training algorithms. So unfortunately, this simple perceptron was decisively proven to only be capable of learning simple linear functions that basically were splitting your data into halves. One test that it failed, and this pretty much blew the lid off it, was its inability to learn the exclusive OR function. This is just a simple 2-input logic gate where the equation is this or this, but not both. That's an exclusive OR, and it could not learn that. It could learn AND functions, both inputs, or it could learn the OR function, but it couldn't learn that this or this, but not both. And that was a real killer. So people describe this in the field as being the first neural network nuclear winter, because for a decade or 2 or 3 after this Minsky and Papert paper and ultimately book came out, nobody could get a paper published on neural networks. Then, in the 80s, the backpropagation algorithm for training was discovered, actually, again, kind of simultaneously by a couple of people. And essentially what backpropagation does is you have kind of a forward pass where you calculate these weights and you see if they trigger a neuron's threshold, and you can take it through multiple layers. But backpropagation lets you then look at the error output, compare the output of the neural network against your desired output, and then take that delta, that error value, and kind of propagate that back through the network, taking the derivatives basically of the error at each level and apportioning it across all the neurons leading to that output, and thus adjusting the weights and training it. It takes many, many repetitions of the data stream through this training process where you do a forward pass with the inputs compared to the desired output, and then train the network to adjust the weights. And it's called a gradient descent learning algorithm, kind of the error. You can think of the equation describing the error as being some multi-dimensional curve or surface that's defined by the set of your inputs. And what you're trying to do is take baby steps toward minimizing that error, and getting to a point where finally you're at hopefully a reasonable minimum level in the error. And of course, there's all, these are not simple shapes, and it's possible to find yourself in a valley that is not the minimum point. It's what's called a local minima, and that would be, it may be acceptable if it's a good enough result, but it might be unacceptable if it's not. So there was a significant hype cycle. People were designing hardware. People were trying to commercialize this. And then generally it was proven that except for one or two pretty specialized applications, in almost all cases, other machine learning algorithms or statistical methods that were much better understood, had a stronger mathematical basis, were more deterministic and reliable, outperformed neural networks. Neural networks could get up to the 70% level that these other methods could get to 100%. And at that point, basically, we entered the second neural network nuclear winter, and it became impossible to get a paper published or to get funding for research on neural networks for several years. So obviously, we're past that now. There's a new hype cycle. It's pretty clear if you look at the news, if you follow this. There's a lot going on. This is a field that now is growing exponentially, about an order of magnitude per year. So it's really rocketing. So what's different now? Is anything different? Well, there's really three things. If you talk to researchers, like famous researchers who now work for big companies like Andrew Ng, who was at Stanford, now is at Baidu, they have the same story. They say there's really three factors: more data, lots more data. The training sets are orders of magnitude larger than the biggest training sets anybody ever tried to train a multi-layer neural network for, back in the 80s. There are better models, so that the networks themselves are more sophisticated. They have many more layers. Instead of that simple three-layer network, and believe it or not, most people were just using that simple three-layer network in the 80s and early 90s. Now, recently I saw Microsoft is using neural networks with over 1,000 layers. So these networks now have millions or billions of parameters, weights and connections associated with them. So they're huge. And the training time on some of these would literally take months if it wasn't for really powerful compute capability, very cheaply available. And this happens to be where NVIDIA enters the story. GPU graphics processors have evolved from just painting pixels, a massively parallel operation for gamers, they became programmable, about 10 years ago in order to do, more cool effects with the shaders. And people realized, hey, we can do general purpose computation with those, and they're so incredibly parallel, and they have such high bandwidth, we can get about an order of magnitude higher performance out of those than we can with standard CPUs. And it just happens that GPUs are really good at matrix multiplies and matrix vector multiplies, sparse and dense. They're just really great at that because that's basically what most computer graphics operations are. And so NVIDIA really fell into it because this is now a really growing business for us. It's already becoming more important to us than what was our traditional supercomputing business just 2 years ago. And it's probably going to be the first business to come along in a long time that's going to challenge conventional graphics and gaming as being our main business. Prior to this, my business, the Tesla high-performance computing, put high-end GPUs in supercomputers business, was only about 10% of NVIDIA's business. Potentially, in 10 years, you could look at deep learning and see that it's half or more of NVIDIA's business. And this is because of the fourth factor. This is why I don't think this current hype cycle is going to result in a nuclear winter. There are immediate financial rewards, huge ones, that can be almost instantly deployed by these massive companies that have these cloud-based applications that are providing us all of these services, mostly through our mobile devices, but through our desktops, tablets, whatever. So, for Google to be able to look at every uploaded YouTube video and actually watch the video in faster than real time and figure out that, oh, this one's about a tractor pull. Oh, this one's more cats. And be able to add some metadata so that when you search YouTube for cats or tractor pulls, that it's going to pull up those videos as candidate videos. That's huge. That means that you're going to be more likely to be searching on YouTube, and they're going to be able to serve you advertisements based on the content of the video, which represents, it's an indicator of your interest in it. So all these companies, like Facebook does a build every week and a release of their software, rolls it out across all of their servers once a week. And so every incremental step they make in improving the ability to tag your friends in photos or to understand what your interests are, those are things that they can roll out the next week. And so this has been a huge economic engine. All of these companies and more, there are now hundreds and hundreds of startups that are receiving billions and billions of dollars in venture capital funding, all related to AI/deep learning/machine learning applications. It's bigger than plastics at this point. And these companies have essentially hoovered up all of the researchers in all of the universities all over the world in order to bring this expertise into their companies. They back up to somebody like Andrew Ng's house, and they have a cubic meter of cash in the back, and he hops in and drives from Stanford to the new Silicon Valley Baidu Artificial Intelligence Research Laboratory. And that's good and maybe bad, but it has a side effect. All these researchers, because it was a seller's market, and they wanted to keep publishing. Most of them have kept their university affiliations. Andrew Ng heads up Baidu's Silicon Valley Research Lab, but he's still a professor on staff at Stanford as well. And they've all kept the right to publish results. So it's a very open community. If you have an internet connection and you have access to archive.org, they're publishing in freely available journals, if you will. The people are making videos of conference proceedings, et cetera, all available. People are publishing their algorithms and they're publishing their tools, open sourcing their internally developed frameworks for deep learning almost as fast as they're building them. Certainly they're reserving some capabilities for their own use, but right now this field is limited. The growth rate, as fast as it is, it's entirely limited by a vacuum of human capital, people who actually know anything about deep learning. And this is going to persist for a few years. So there's a huge opportunity here, I think, both for the university and for individuals. So it's affecting a lot of different areas. So let me just run through a couple of weird cases. Some of these are interesting. So Baidu describes Google as the Baidu of the US. You would call Baidu the Google of China. They have literally 1 billion users. Almost all of them access Baidu on mobile. They have a visual search. You can take a picture of you or your friend, and they will deliver back 100 or 1,000 people who look just like you, or celebrities who look like you, or celebrities who look like your dog. You can take pictures of a garment, and they will take you to a shopping site that is selling that garment. Take a picture of it on a passerby. You can upload a photo that you took of some pastoral scene, and they will deliver back hundreds of pictures that look just like that. They're also arguably the leader in speech recognition right now. They have something called deep speech, and it uses something called a recurrent neural network. Normally, neural networks are kind of this one-direction thing, feed forward through, except for the training, propagation of the error. They don't really have a memory. Recurrent neural networks feed back some of the outputs back into the inputs, and it gives them the ability to do temporal dimension processing. So they're actually capable of looking at a sequence of noise and splitting out that it's individual phonemes that they can then fit into utterances and assemble those into words and give you a speech recognition out the backside. And so Baidu is one of the leaders actually in what's called end-to-end neural network speech recognition. And this has been a pattern. All these people have been working in all these areas like speech recognition for decades, hand constructing feature recognizers and signal processors and parsers and classifiers and all these things, programming these things for their whole career. And when they first hear about neural networks and how successful they're being in some other application area, I got to stop doing that or I'm going to dump my laptop. Their first impulse is to say, well, that might work for this center part. We've got really good processing at the beginning. I think we can replace the classifier portion in the middle. What quickly happens is that they discover, well, that signal processing you were doing up front to do an FFT, to turn it, and the classifier, you can basically just go end to end. You can get rid of the whole thing if you have an appropriately large and appropriately architected neural network. But the big problem is getting labeled data. There's kind of two general classes of training. One is supervised, meaning you're giving them data and you know what the right answer is so that you can train them. And then the holy grail is something we're not very good at yet, and that's called unsupervised learning. That's where you can basically just turn a neural network theoretically loose on a really large data set, and it's going to discover structure and generalize. Like if you were just let loose in a big building, full of stuff, and you have to wander around and decide, oh, this is a cafeteria, oh, this is a department store. You have to figure that out yourself without anybody telling you what it is. That's what people want to be able to do with unsupervised learning with deep neural networks because of the difficulty of getting reliable labeled data. So what Baidu did was actually fairly clever. They had several different collections of data, and then they actually multiplied the size of the data by distorting it, by adding noise, by overlaying data on data, and by stretching and compressing the time dimension of it, changing the pitch. And so they artificially multiplied the data to make it more like if you were, instead of trying to listen to a person talking into a microphone in an otherwise quiet room, to trying to eavesdrop on a conversation in a bar, for instance, a noisy bar. And as a result, they've had to go with really large networks, really large recurrent networks. They've had to innovate in training using multiple GPUs in parallel in order to accomplish their training in an adequately short amount of time. But their results have been fabulous. They, right out of the gate, beat all of the other major speech recognition efforts at other firms. And today, they use the same neural network to do speech recognition for Mandarin as for English. So it's actually a very flexible architecture. And it's now more accurate than people. Again, achieving superhuman results when compared against tests where they're asking people to try and listen to a recording and transcribe what was said. So it's getting really good. And if you've been using speech recognition on your smartphone over the last 3 or 4 years, you've probably noticed the difference as well. I know, I can be driving down the freeway with the windows open on my windsurfing van, which is old and noisy, and I can yell at my phone, and it gets it right. It's amazing. Deep learning is also exploding at Google. This is a recent chart that they showed, basically just looking at all of the directories that the developers were using and looking at how many of them had included the deep learning framework and were using that as part of the checked-in development, code development files that they checked in. And they are now over 2,000 applications or internal applications and projects at Google are using deep learning. And they're using this for everything. They're using this as Gmail. They're using this for image understanding, for getting better directions in maps, better job of estimating how long it takes for you to go from point A to point B, to understand your speech, do translation. I already talked about YouTube. They're trying to not only understand Google Earth, so they have all of the cars that have been driving around accumulating all of these street view pictures. They actually are processing all of that using deep neural networks to cross-reference street numbers, house numbers, and make sure that they know where they are and try and correlate and do a better job. But they're also looking at all the signs because they want to be able to help give you directions to a place. Or if you say, hey, I'm looking for some place that has electronics for the lowest price near me. They want to be able to steer you to that just by extracting the information from the street view. And they want to be able to add captions to photographs. This is part of kind of the tagging process, but it's also making it human readable tags so that you can start to understand why they gave you some photos, right? So these are all generated by the neural networks. This is now a year old, but you can see most of these are really good. This one's a little incomprehensible. That's obviously not a man flying through the air while riding a snowboard, but you can kind of see how a neural network might have been fooled into thinking that's what it was. Google's also a leader in having neural networks start to interact with the world, not just process data from it, but also provide some real-world feedback. So they acquired a group in London called DeepMind, who famously taught neural networks to using something called reinforcement learning, which is where you reward the network for making progress toward a goal that has not yet been achieved. so it's a little tricky. They've taught it to play a bunch of Atari games, old Atari video games, most now at superhuman levels, better than the best human players. And so, initially when they were training this is a video that Jeff Dean showed at GTC a year ago, our graphics technology conference. And you can see it's pretty lame. But after training, it's awesome. It not only knows how to hide, but it never misses. Every shot is hitting something. And it makes, some amazing shots. I notice it picks off a lot of the invaders in the back row first, just so the front ones don't know they're being picked off, I think. And that shot of that flying saucer was nothing short of amazing. Space Invaders and Atari games maybe isn't that important, but the same group essentially is the group who used neural networks to build AlphaGo. And this is, recently in the news you probably heard that this computer program, kind of like the computer finally beating the chess master, not only defeated the top UK champion initially, 5-0, but then beat someone widely recognized as the best Go player in the world, beat them 4-1. And so, superhuman capability on a problem that experts, computer experts, based on the fact that there are so phenomenally many possibilities that Go could not be analyzed, if you will, just exhaustively analyzed. You couldn't use the speed of a computer to just kind of search ahead at all possible moves and win that way. It had to use some kind of strategy and some kind of intuition, human-like, if you will, in order to be able to successfully play Go. And people thought it was going to be at least 10 years into the future before, maybe 100, others thought, before computers would be powerful enough. And the way this happened is there have been many Go games played and reported. And so they first built a neural network, and they fed all of those games into AlphaGo. Then they had AlphaGo play Go against a copy of itself, essentially replicated it and let it play millions of games against itself before letting it play people. And it's very good at that. We're also seeing deep learning appear in robots. And probably the first robot almost all of us are going to own is going to be an autonomous vehicle. And deep learning is now the basis of pretty much every automotive company's assisted driving on the path to autonomous vehicles program. So being able to identify everything in a scene correctly and understand what's a shadow in the road, what's a person, what's a tree, what's another car, even being able to do it in bad weather, being able to do it when there's not really very much contrast. These are very hard problems, and they're now being solved. NVIDIA actually, I was talking about the end-to-end approach. A few years ago, DARPA sponsored some of the first attempts at autonomous vehicles. And so they had this DARPA Autonomous Vehicle acronym DAVE. So NVIDIA built this DAVE 2, and we're still training it. But it started with just building a box. So we've got this NVIDIA box that we call the Drive PX. It's GPUs and a bunch of camera inputs, and you can have radar inputs and things like that. But we basically just hooked it up with the steering wheel. We wanted to teach a neural net to steer the car. And so we basically just let people drive around with this with a few cameras. And then we built a neural network, a big neural network, and a simulator that took all of these hundreds of hours of video of people driving, doing a reasonable job driving, and the only sensor besides the video is the position of the steering wheel that the person was turning. And we basically ran all of that past the neural network repeatedly. And then we allowed the car to essentially, in feed-forward moment, we allowed the neural network to drive the car. And initially, started in February of this year. We did some testing with just a little bit of training, and it could drive in a straight line. This is in New Jersey, a blocked off road by the office there. You can see the guy's got his hands out. But when you took it in some different conditions, it actually was scary dangerous. Shying away from things like shadows and almost driving into parked cars and things. But just 3 months later, after 3,000 miles of training, it got pretty good. Just push go, push on the accelerator, and it stays within the cones just fine. Good enough that you feel comfortable texting while you're driving, right? And it does well on roads in all conditions. It's no longer shying away from shadows. They feel confident enough to take it on a highway with other drivers, even where there's no lines on the road, even when there's no road. And this is end-to-end. The only input it has is what came from the cameras and the position of the steering wheel. So that's pretty cool and pretty exciting. If you look at all the different areas, ImageNet and all these things, obviously, AI, this is a really big thing. And it's already improving our lives, right? Better speech recognition, better recommendations, et cetera. Those are all really good things. And as a result, it's showing up everywhere. There's lots of people using it to analyze images of mammograms. And they've already trained neural networks to do a better job than trained humans to recognize tumors. They already have the information of whether or not the biopsy was positive or not. And that's the training set. And if you get a large enough training set and a large enough neural network, you can do a pretty good job on things like that. So why GPUs? Well, because GPUs can shorten the training time. It's because they have huge memory bandwidth, huge capability. And obviously, if you can reduce the training time from 6 days to just a day, that's a really big deal, especially when we have this dearth of qualified people. You want them to be as productive as possible. And so, spending money on good tools is a good idea. So NVIDIA is actually going upstream, motivated by the potential market here. We've built a new computer, just huge capabilities, all in service of deep learning. We've written optimized libraries. We're accelerating all of these frameworks that all these companies and organizations, a lot of universities. We're basically underlying all of these. Probably 95% of the machine learning work that you read about today is all being done on NVIDIA GPUs. So, we're really lucky. And what does it mean in terms of money? This is actually a non-supervised learning case. This is from 2012, a bunch of people from Stanford who now work for companies, analyzed millions of images that were randomly pulled from YouTube videos, still frames. And then they went back into the network after letting it chug on this for days. And the network was immense at the time, although now this would be considered a modest-sized network. But it was 1 billion connections, 10 million images. They used 1,000 servers at Google with 16,000 cores and took 3 days. And a year later, a couple of people from the team just took 4 servers with 12 GPUs and basically did what essentially was $5 million and 600 kilowatts worth of computing, 4 kilowatts and about $33,000. You can do this in your basement. So really huge, and the performance scales really well. So how does deep learning touch your life? Every way, and it's going to continue to do so. It's going to be in your home. You're going to be in it, in your car, et cetera. So all the applications, all based on GPUs. So I couldn't resist adding an epilogue because I'm a supercomputing guy. And people think about deep learning and they go, well, what does it mean to me? And all the people I talk to are in the supercomputing world. And they say, well, maybe I can use deep learning to analyze that big data set that I generated with my simulation, and I can find some associations or learn something from it in a way that's going to make sense. Supercomputing is a hard business because we have really big aspirations. We try and increase by 1,000 times every 10 years. We went from a megaflop to a gigaflop to a teraflop to a petaflop, and now we're setting our next sights on an exaflop. But 3 orders of magnitude hops is a lot, right? It's the difference between crawling coast to coast and taking a business jet. But when you look at that 10 to the 18th floating point operations per second, this is the top 500 list. It's the 500 fastest computers in the world. The green line is the sum of all of them. This is a log-log graph. Here's an exaflop up here. This is the fastest, the #1 computer, and so it's kind of stair-steppy because the computer gets installed, right? And this last one here is the last system on the list, the bottom of the list. And you can see all these are on about the same slope. And so, you can kind of look, and this was when we achieved 100 gigaflops in a supercomputer. This was the teraflops. These are each 10x the prior record. So, there's not very many fields, in fact, there aren't any, that advance this rapidly over decades. So we reached a petaflops in 2008 and 10 petaflops in 2012. Where's our 100 petaflops? We should have it by now. It should have been here about 2014. But if you draw straight lines through these curves and look at the slope, you see that something troubling is starting to happen here in the last decade. What's happening is Moore's law is dying. And it started about the middle of the last decade. And we're still getting the transistors, but we can't really afford to turn them on anymore because the power is now not scaling the way it used to. And this is something called Dennard scaling, and I'll talk to you about it. But this is the point where Intel said, for instance, we can't increase spec int of a single processor anymore. We can't make a single processor go any faster, and so we're going to go multi-core. And we're going to back off from all of these special features we've been putting in to try and make a single thread go really fast. So this period here, this is the death throes of Moore's law. I call it the weekend at Bernie's phase of Moore's law because we're trying to extend the life of Moore's law. So the first thing to go was voltage scaling. Every one of those steps in Moore's law, we were dropping the power supply from 5 volts to 2 volts to a volt, and now we're getting down close to what's called the threshold voltage. And the basic characteristics of CMOS are that as you lower the voltage, the leakage current starts to go up. So this is kind of the fraction of your watts. You can compare those two lines and say, what fraction of my watts is due to me actually getting active work done because it's switching energy, and which is just leakage, which means I'm too close to the threshold. Plus, communications has gotten really expensive. To actually do a full 64-bit double precision floating point add multiply costs about 20 picojoules. It costs twice that just to read the operands out of an SRAM on a chip. And it costs it actually costs more than that to just go a millimeter with that data on chip, much less halfway across the chip, which costs an order of magnitude more. And don't even talk about going corner to corner on the chip or going off chip. These are really big numbers. Plus, our memory is becoming an increasing percentage of the power of the chip. And we're power limited. We have a particular envelope, a certain amount of energy we can cool from a chip, and a certain power budget that people design into servers. And you can see as more and more of it goes into things like leakage and memory, we start to have a real problem. So when you look ahead to an exascale system in 2020, which is when the Department of Energy wanted to procure it, they've been buying the world's largest systems. We go back and look at the 20 petaflop system that they have in 2013, and you look forward and you look at the Moore's Law energy scaling, and you say, well, we're going to be off by about a factor of 25 of the energy efficiency we really want. So in the meantime, DOE has pushed back their plans for an exascale to 2023 instead of 2020. Well, Moore's Law isn't quite dead yet, but it's getting pretty anemic. There's things we can do. We can use bigger transistors, and that they're bigger gates. Even though we have finer lithography, we can sacrifice switching speed for lower leakage. When you do that, that might be a really good trade-off. If you have lots and lots of parallelism, that might be a really good trade-off, because there's about a factor of 100 from this short gate length, really high-speed transistor to these long gate length, slower transistors. It's like, a factor of 100 in the leakage current, but the delay only goes up by about a factor of 2. So if you have a lot of parallelism in your chip, that's a good strategy. And that's what we do with GPUs, because we have a lot of parallelism. So you can actually see here, this is 3 generations of GPUs that all happen to be implemented in the same technology, 28 nanometer. And you can see that the energy efficiency on single precision arithmetic actually increased over time, even though the Moore's Law technology stayed the same. But there's a possibility for something even weirder to be exploited. And that's using deep learning to actually do the science. If you look at the flagship scientific applications that DOE is using to justify really large computers, petascale and exaflops, it's material science, it's climate change, biofuels, things like that. And if you look at these things, they all have a certain amount of chaotic nature to the physical phenomena you're trying to simulate. And yet, one of the biggest challenges to building an exascale system is having it be perfect, and that it has to run perfectly without a single bit getting inadvertently flipped in this massive machine running millions of threads at this horrendous speed for weeks, maybe, to solve some of these problems without a single bit error. This is a really huge problem, and it's kind of, in my mind, it's a really interesting tension between the chaotic nature of what we're trying to simulate and the absolute perfection that's necessary for the system in order for our applications and our algorithms to run error-free and to converge accurately, et cetera, with no errors, not give us wrong answers. So there's actually something really interesting some people are experimenting with, and that's using machine learning to actually approximate these solvers that are sometimes a little bit fragile, a little bit fussy, a little bit sensitive to how big of a timestamp you have, and they're difficult to scale. So this is actually some people at ETH in Switzerland took Navier-Stokes. This is fluid dynamics, computational fluid dynamics. And they used the explicit solver. They generated hundreds of millions of labeled data points. This is a particle simulation of fluid, and they want to have millions of particles. And they used Navier-Stokes, the explicit solvers, looking at compressibility and viscosity and all these things directly. But they used that to generate a data set. And then they trained a random forest machine learning algorithm on that data set. And they were able to achieve a speed up of up to 3 orders of magnitude, because once it was trained, the inference-only mode was 3 orders of magnitude more efficient in terms of computational intensity than the direct solver that they used to train it. So like here's a video then showing the one on the left is the fake one. It's the approximation. The one on the right is the actual particle-based fluid simulation. And actually, to my eye, oh, and this is, by the way, it got so fast they could interact with it in real time. So this is them real time moving the mixing the fluid. They have a couple of different fluid types, and this is real time. Previously, it took about a couple hours to generate like 30 seconds worth of video. So that's an interesting idea, and it could mean that if this could be applied to more kinds of simulations, that we could effectively solve problems at exascale problem size, at exascale speed with today's petaflop systems, or maybe even more efficient. There's one more example from the molecular modeling world. These guys, some Germans and the like. There's an interesting paper. They're tackling this problem of trying to approximate Schrodinger's equation and understanding, the atomic contributions to a molecular, to a molecule, and what they've proven is that with a large enough training set that they were actually able to have a machine learning model that did a better job, that was more stable, because the underlying equations here, and I'm not a physicist, but the underlying equations were unstable. It was difficult to use them on large complex molecules, and they were actually able to make meaningful predictions with a smaller error rate than some of the classical methods. So one last paper. This is my last slide. So is this the future of high-performance computing, where we have some number of modest-size, kick-ass training machines, because training is really data-intensive, and then we have some number of super power-efficient inference-only engines? Inference is really cheap. Once you have your model trained, often you can fit it in a cell phone or a mobile device, and you can solve meaningful problems with it, like recognition, controlling a drone, in something that's only a few tens of watts, or only a few watts. So what we've actually discovered, this is a paper actually one of our interns with some people in NVIDIA research put together, and it's basically looking at how cheaply can we possibly do inference. Unlike training, inference is really robust to compression. And so what they've done is they've pruned the network. You basically look at the network once it's trained, and anywhere there's a near zero weight, you can just delete that connection and not even ever have to look at it in inference-only mode. And they have compression techniques that they apply to the weights. They have basically, these numbers at the bottom here are basically looking at that 5%, for instance, means the compressed model is 5% of the original data set size. So they're achieving some really large compression rates. And then what they do is after pruning, after compressing, and there's a few other things that they do, they retrain the network as they're doing that. And they actually achieve error rates. These are the compressed errors. And their compressed errors are the same or even slightly lower than the unpruned, uncompressed, unretrained network. And the energy and performance improvements are huge. This is comparing, these are all different deep learning test cases. AlexNet, here there's a couple different versions of that, 3 different versions of that. That's that ImageNet competition. And the first line here is speed normalized to a conventional Xeon CPU. And you can see we're comparing the CPU dense, CPU pruned and compressed. We get a nice 2x, 5x kind of, this is energy efficiency improvement, this is speed up. And then running on a GPU, we're up to 20, this is a log scale again, up to 100x faster. And you can see some of these things are getting up to 100 times less energy than running it on a CPU, or 135 times faster than running it on a CPU. So you can imagine training a model for combustion, for instance, and then taking that trained model over to something like this, and basically having an array of very energy efficient nodes that would accomplish the computation for just a tiny fraction of the cost of using the normal explicit method. So my challenge to any computational scientists and data scientists out there is go find more of these, because this could be a really profitable direction for research. And that's my last slide. Right. I think that's definitely one of the concerns, right? And so, I think that there's a certain amount of validation of models that can be done at smaller scale. I mean, oftentimes, you're looking at a certain package of physics, and if you're looking at it and its behavior in a certain volume, for instance, applying it at a much larger scale might be computationally untenable, but if you validated it at a particular scale, it's the same science, only over many, many more copies of that domain. There's other algorithms that probably you can't say that about. And so, there's probably some statistical analysis looking for, distribution of behaviors over a particular data set or whatever, that kind of analysis probably needs to be developed to be able to measure how good your model is representing the science. But that's definitely one of the problems with it.
One question. The speech recognition, is it connected words or isolated?
No, it's fully connected, just natural language. You can speak just as I am. It's pretty amazing.
Any other questions? Well, let's thank the speaker.
Thank you.